So Cocoon is the first IFC approach, information flow control approach, for an off-the-shelf language that does not require modifying the language or compiler. So let's start with a motivating example. We have two users, Alice and Bob. Alice and Bob would like to find how many possible times they can meet, how their calendars line up so they can actually meet with each other. They would like to send their calendars to a piece of code, denoted by the orange circle here, that finds the shared availability and returns the number of possible meeting times. However, what Alice and Bob do not want is for this code to send back, sure, the number of possible meeting times, but also Bob's entire calendar to Alice, or for that matter, to anyone else. Bob's calendar should only go to Bob, and Alice's calendar should only go to Alice. We don't want this. So one approach that can be used for this is access control. Access control could block off the flow of information and say, okay, well, Alice and Bob can't send their calendars to this code that could be doing bad things. However, in that case, then Alice and Bob can't find what days they can meet on, how many days they can meet on. They can't do what they want. It limits things too strictly. An alternative is access control could say, okay, fine, it can go ahead and pass through, and then great, Alice and Bob can send their calendars through, the code can go ahead and find the availability and send it back. But then we once again have the threat model. We have Bob's calendar can be sent through. Access control doesn't discriminate between different types of information. It just blocks off flows completely or allows them through completely. So access control can't solve this problem. Access control can't let us do what we want. An alternative is information flow control, or IFC for short. In information flow control, each piece of data is labeled with a specific level of secrecy. So in this case, you can see Alice's calendar is marked seek A. In other words, it is marked as secret to Alice. Only Alice should be able to read her calendar. Similarly, Bob's calendar is marked seek B. It's secret to Bob. Only Bob should be able to read his calendar. In this model, in the way IFC would tackle this problem, the code goes ahead and computes the availability. It's allowed to read both seek A and seek B. And then it spits out the number of possible meeting times marked with both Alice's and Bob's secrecy labels. Notably, because seek A means only readable by Alice and seek B means only readable by Bob, seek A and B means readable by no one. No one is allowed to read it. It is secret to everyone, which means no one can read it. So in the IFC approach, this secretly marked number of possible meeting times is sent out to another piece of code denoted by the green circle that declassifies it, lowers the secrecy level, and returns the number of possible meeting times marked with Alice's secrecy to Alice and marked with Bob's secrecy to Bob. So in this case, exactly the data that we want to get across is coming across. The calendars are going where they need to. The number of possible meeting times is going where they need to. Everything is functioning. So what if the bad thing happens again? So the availability finder sends across Bob's calendar. Bob's calendar is still marked with secrecy B because you can't just take off secrecy labels without explicitly declassifying. It gets sent to the declassifier, and the declassifier looks at this and says, no, this doesn't match what's supposed to happen. No, we're not declassifying this. And the threat stops there. So information flow control lets us do what we want. It lets us tackle this problem. It lets Bob and Alice keep their calendars private, but share their availabilities. So some prior work enforcing IFC. The first type that I'm going to discuss is interprocedural analysis. Interprocedural analysis is generally done after code has been written. It's generally done analyzing already written and produced code. It walks through it and analyzes it to see how does the information flow, where does it go, how does it move. The problem with interprocedural analysis is that it's non-compositional. It doesn't really preserve context very well. It tends to forget or not keep track of how information is going outside of the specific context being analyzed. With multiple different contexts, this means that it kind of has to assume the worst case scenario, and things get marked with higher and higher secrecy labels. And what tends to happen is everything gets marked as super high secrecy, even if it doesn't need to be. This is obviously bad. This isn't what we want. This isn't the best approach. An alternative is dynamic analysis. Dynamic analysis is performed at runtime. This lets it go ahead and keep track of the context. It lets it pass data back and forth between different contexts and keep track of exactly what's going on. Great. The problem is it's at runtime. This means high performance cost. This, again, is a problem. We don't want to slow down our CPUs. We don't want to add overhead to perform IFC. The final approach that I'm going to discuss here is type-based analysis. Type-based analysis is similar to dynamic analysis in that it often involves modifying the code itself, modifying the code to explicitly handle information flow control. It keeps track of context, lets the program keep track of where the context is, where the data is going, where it's come from, what its labels exactly are. The problem with type-based analysis is that it requires modifying the language or compiler with one exception, Cocoon, which is what I'm talking about today. Cocoon, again, is the first IFC approach for an off-the-shelf language for Rust that doesn't require modifying the language or compiler. Cocoon is implemented as a library in Rust, and programs that use Cocoon import the library and then modify their code or write their code in the first place so that it uses that library. So let's back up and talk about that motivating example again. To remind you, we have Alice and Bob want to send their calendars to a piece of code, find the shared availability, and tell them how many days they can meet on. How would we write this example with Cocoon? Well, to start with, we have Alice's calendar and Bob's calendar, both represented by hash maps, with an example entry in the hash map up to the right there. So you have Monday mapping to a secret value, secret true, or to secret false for Bob in this case. Secrets are denoted by, or secrets are handled by, they are wrapper types around a piece of data. So in this case, a secret holds a Boolean and a static type. You can see it there as lat A or lat B. These static types represent the labels. So lat A in this case represents Alice's secrecy label. Lat B represents Bob's secrecy label. These are static types. It marks the data as secret to that level and preserves secrecy. So again, in this example, we need to initialize a counter. The goal of this is to count how many days can we meet on. So we need to initialize a counter. This counter needs to be able to interact with secret data. So it needs to have a label of AB. It needs to be as secret as Alice and as secret as Bob's data. So we create it using a struct or a type of secure code region called a secret block. A secret block has an associated secret label, in this case AB. And inside of a secret block is where you can interact with secret data. In this case, we're creating a new secret by calling wrap secret. There are a few functions that can only be called inside of secure regions, as in they will not work if called outside of secure regions. Secure regions specifically handle the code in such a way that it gets turned into an appropriate call and can be used. If you attempted to call wrap secret outside of a secure block, you would get a compiler error, nothing would happen. So we've created our counter. Now we need to iterate through the days in Alice and Bob's calendar. So we iterate through Alice's calendar and we use another secret block. Again, it's interacting with both Alice and Bob, so it has label AB. We need to perform a check. We essentially need to check, is Alice available, is Bob available? We have Alice's availability here, although it's secret, so we use unwrap secret. Is Alice available? Okay. If that's the case, we then need to query Bob's calendar using hashmap get and option unwrap. This returns a secret of Bob's availability, and we use unwrap again to check if Bob is available. Great. Then, if they are both available, we need to increment our counter. So we use unwrap secret mute ref. This just means that we are able to mutate the variable that's getting unwrapped. So we pass in the counter and we increment it by 1. This loop continues, passes through all the days, and at the end, we want to return how many days there are. So we need to explicitly declassify. Declassification is the one area that needs to be audited in this code for us to verify that it works properly. One of the major benefits of information flow control is done properly, it greatly reduces the trusted code base. With this code written in Cocoon, none of this code needs to be audited, none of it needs to be trusted, all of it will guarantee secrecy, except this last line where you are explicitly declassifying. So you need to make sure am I actually declassifying what I'm supposed to? But beyond this, all of this can be trusted. So let's talk about some of the threats that we had to handle. And all of these are handled and discussed in greater depth in the paper. So I'd recommend you take a look at that for any further curiosity you have. But I'll run through a few of them real quickly. So first of all, what if we try to do this? What if we initialize a variable outside of the secret block and it's not secret, and then we try to increment it inside? Well, we don't want that. That is just explicitly passing secret data outside. This is prevented via using Rust's type system and procedural macros system. We can use some of the particular features of Rust to disallow this behavior. And again, more details are in the paper. Second, we want to disallow function calls that could have side effects. In this case, we don't want it to write to a file day available every time a day is available. This is, again, explicitly violating information flow control. Again, we prevent this using types and types and procedural macros. In this case, the result is that no functions except for ones that we explicitly know are safe can be called inside of secret blocks, as in the macros will not compile and you will not be able to write code that does this. Finally, there is a particular set of side effects inside of Rust that is invisible. So what if we made our counter implement a type or implement drop specifically, so it has a custom destructor? When it gets destroyed, I didn't include it here for space, but say when it gets destroyed, any piece of code could be inserted here. We could have a print line, we could have it do whatever we wanted. We could have it print out everything that's been done. Again, obviously bad. And again, handled via procedural macros and type specifications. Rust is pretty cool, in case you didn't know. Lets us do some neat stuff. So let's move on to the case studies for Cocoon. So with these case studies, our goals were to test the usability of Cocoon, to test that Cocoon is incrementally deployable, as in you don't need to rewrite an entire several thousand line program if you need to keep one thing secret in one place over 50 lines. You can just alter those. Finally, we wanted to test the performance overhead. Our main claim to improvement over dynamic analysis is that we don't have performance overhead, so let's make sure that's true. So we implemented Cocoon as a Rust library, took real Rust programs, added Cocoon as a library, and then modified those programs to use Cocoon. First is Battleship. Battleship is to test incremental deployment. This is a game where two players are competing against each other. Each player has secret information and is trying to guess the other one's secret information. So we want to protect the secret data, but allow the guesses to go through. So we need two-way flow of data, but two-way flow of specific data. This is also based on some prior work that was done in the GIF paper on information flow control a while ago. So we built this, it works, and there was no runtime overhead. Next is Spotify TUI. This is a real-world program. This is a text-based Spotify interface, so a way to interact with Spotify from your data terminal on your computer. We wanted to protect the user authentication secret, something equivalent roughly to the password that lets Spotify know you are you. We did this, it works, and there was no runtime overhead. And finally is Servo. Servo is another real-world program. It is a web browser and rendering engine, very popular Rust program. At the time of the paper's writing, I believe it was top 10 most starred project on GitHub written in Rust. As of 2 days ago, I think it was 29th, so it's fallen a little bit, but still very popular. And for this one, we wanted to protect HTTP responses from cross-origin readers. In other words, if you're entering your data onto a web form and there's an ad on that web form, that ad shouldn't be able to read your data. So we did this, it works, and again, there was no runtime overhead. So in conclusion, Cocoon is the first IFC approach for an off-the-shelf language that does not require modifying the language or compiler. Thank you.
Thanks, Vincent, for 1 o'clock. Any questions?
Hi, thanks for the talk. You carefully avoided having to modify the language or compiler. What I'm wondering about is, suppose you relax that restriction. There was a bunch of sort of explicit code in there dealing with secrets. And obviously, or presumably, you want to explicitly declassify. But the other code, I wonder whether you maybe want to do that implicitly, and if you've thought about what that would look like.
I'm sorry, I think I missed the last sentence. You were saying, I wonder if, and then I missed the rest of it.
I wonder if the operations involved in secrets, other than declassification, might be better if done implicitly, rather than explicitly via function calls, macros.
It could. Can you please repeat the question? Certainly. Let me, please tell me if I'm getting this wrong at all, but I believe the question was, if we relax the restriction on we don't want to modify the language or compiler, would it be better to try to make operations on secrets, non-declassify operations like adding 2 secrets or subtracting 2 secrets or something like this, make those implicit, so don't require actually adding all that extra code, the secure blocks. I could see a case where that could be significantly easier to write at the very least. It would require almost certainly modifying the compiler. But yes, I could see where that would ease programmer burden. The main con would just be it would require modifying the compiler, which we are trying to avoid doing because modifying the compiler significantly impairs how easy it is to adopt for your average programmer.
Thank you.
Certainly.
Thank you for the talk. It's really cool. Just one small question. Do you support async code, which would put all the variables on the stack?
I do not believe we do.
Okay.
I'm not willing to swear to that. I'd have to go check exactly, but I do not believe we support async code.
And would you recommend that people compile their code with abort on panic?
It could depend on the goal of the code being compiled. Probably for release code, you want to compile with abort panic on. Actually, it shouldn't matter. The way Cocoon handles panics is Cocoon actually instantiates a new panic handler for every secure block. So panics from inside secure blocks get caught and handled in a custom Cocoon way that doesn't cause problems.
That's cool. Thank you.
Certainly.
Hello, thanks for the talk. So did you find any real-world programs where you could not use Cocoon because you are disallowing some features, right, because of the side effects and so on?
I don't believe that we came across many programs that we couldn't use Cocoon on for that reason, for the things that we're disallowing. We did have a number of programs where it was tricky to use Cocoon at times just because not every program has an obvious policy, has an obvious thing that's secret that we want to preserve. But no, we didn't really come across any programs where the restrictions imposed by Cocoon caused problems.
Okay, thank you.
Certainly.